Spirograph is a geometric drawing toy that produces mathematical roulette curves of the variety technically known as hypotrochoids and epitrochoids. It was developed by British engineer Dennis Fisher and first sold in 1965. The name has been a registered trademark of Hasbro, Incorporated, since it bought the Dennis Fisher Company. The Spirograph brand was relaunched with original product configurations in 2013 by Kahootz Toys. History: the mathematician Bruno Baconowicz invented the spirograph between 1881 and 1900. It was used for calculating an area delimited by curves. Drawing toys based on gears have been around since at least 1908, when the marvelous Wondergraph was advertised in the Sears catalogue. An article describing how to make a Wondergraph drawing machine appeared in the Boys Mechanic publication in 1913. The spirograph itself was developed by the British engineer Dennis Fisher, who exhibited at the 1965 Nuremberg International Toy Fair. It was subsequently produced by his company. U.S. distribution rights were acquired by Kenner, Incorporated, which introduced it to the United States market in 1966 and promoted it as a creative children's toy. In 2013 the Spirograph brand was relaunched in the USA by Kahootz Toys and in Europe by Goldfish and Bison with products that return to the use of the original gears and wheels. The modern products use removable putty in place of pins or are held down by hand to keep the stationary pieces in place on the paper. The Spirograph was a 2014 Toy of the Year finalist in 2 categories, almost 50 years after the toy was named Toy of the Year in 1967. Operation: the original US-released Spirograph consisted of 2 different-sized plastic rings, with gear teeth on both the inside and outside of their circumferences. They were pinned to a cardboard backing with pins, and any of several provided gear heels, which had holes provided for a ballpoint pen to extend through them to an underlying paper writing surface. It could be spun around to make geometric shapes on the underlying paper medium. Later, the Super Spirograph consisted of a set of plastic gears and other interlocking shape segments such as rings, triangles, or straight bars. It has several sizes of gears and shapes, and all edges have teeth to engage any other piece. For instance, smaller gears fit inside the larger rings, but also can engage the outside of the rings in such a fashion that they rotate around the inside or along the outside edge of the rings. To use it, a sheet of paper is placed on a heavy cardboard backing, and one of the plastic pieces known as a stator is secured via pins or reusable adhesive to the paper and cardboard. Another plastic piece called the rotor is placed so that its teeth engage with those of the pin piece. For example, a ring may be pinned to the paper and a small gear placed inside the ring. The number of arrangements possible by combining different gears is very large. The point of a pen is placed in one of the holes of the rotor. As the rotor is moved, the pen traces out a curve. The pen is used both to draw and to provide locomotive force. Some practice is required before the spirograph can be operated without disengaging the stator and rotor, particularly when using the holes close to the edge of the larger rotors. More intricate and unusual shaped patterns may be made through the use of both hands, one to draw and one to guide the pieces. It is possible to move several pieces in relation to each other, but this requires concentration or even additional assistance from other artists. Mathematical basis: consider a fixed outer circle of radius centered at the origin. A smaller inner circle of radius is rolling inside and is continuously tangent to it. Will be assumed never to slip on. Now assume that a point lying somewhere inside is located a distance from S center. This point corresponds to the pen hole in the inner disk of a real spirograph. Without loss of generality, it can be assumed that at the initial moment the point was on the axis. In order to find the trajectory created by a spirograph, follow point as the inner circle is set in motion. Now mark 2 points on and on. The point always indicates the location where the 2 circles are tangent. Point however will travel on and its initial location coincides with. After setting in motion counterclockwise around, has a clockwise rotation with respect to its center. The distance that point traverses on is the same as that traversed by the tangent point on, due to the absence of slipping. Now define the new system of coordinates with its origin at the center of and its axis parallel to and. Let the parameter be the angle by which the tangent point rotates on and be the angle by which rotates in the relative system of coordinates. Because there is no slipping, the distances traveled by and along their respective circles must be the same, therefore, or equivalently. It is common to assume that a counterclockwise motion corresponds to a positive change of angle and a clockwise one to a negative change of angle. A minus sign in the above formula accommodates this convention. Let be the coordinates of the center of in the absolute system of coordinates. Then represents the radius of the trajectory of the center of, which undergoes circular motion thus. As defined above, is the angle of rotation in the new relative system. Because point obeys the usual law of circular motion, its coordinates in the new relative coordinate system obey. In order to obtain the trajectory of in the absolute system of coordinates, add these two motions. Where is defined above. Now, use the relation between and as derived above to obtain equations describing the trajectory of point in terms of a single parameter. Using the fact that function is odd, it is convenient to represent the equation above in terms of the radius of and dimensionless parameters describing the structure of the spirograph. Namely, let and. The parameter represents how far the point is located from the center of. At the same time, represents how big the inner circle is with respect to the outer one. It is now observed that, and therefore the trajectory equations take the form. Parameter is a scaling parameter and does not affect the structure of the spirograph. Different values of would yield similar spirograph drawings. It is interesting to note that the two extreme cases and result in degenerate trajectories of the spirograph. In the first extreme case when we have a simple circle of radius, corresponding to the case where has been shrunk into a point, the other extreme case corresponds to the inner circle S radius matching the radius of the outer circle. In this case the trajectory is a single point. Intuitively, is too large to roll inside the same sized without slipping. If then the point is on the circumference of. In this case the trajectories are called hypercycloids and the equations above reduced to those for a hypercycloid. See also, cyclograph, Ghiaccia copyright, harmonograph, list of periodic functions, pantograph, spirograph nebula, a planetary nebula that displays delicate, spirograph-like filigree. References. External links, official website, in Spirograph, a web-based, interactive spirograph replica, HTML5 interactive spirograph creator, a spirograph software for Miss Windows, Kahootz Toys, Super Spirograph manual in French, German, 1979.